zero, meaning it's a natural object, like a comet, for sure.
Professor Avi Loeb from Harvard University once suggested that 3I Atlas was breaking into many pieces like a normal comet. But recent observations reveal the exact opposite. The third interstellar object in history is not falling apart. It looks as if it is rearranging itself, forming structures that have direction and rhythm. These unusual shapes and the way they change over time force us to ask whether this is just a drifting object in space or something more advanced, possibly guided by technology we have never seen. Scientists are still searching for answers. I cannot solve every mystery either, but in this video, I will show you the latest transformations of 3I Atlas and reveal the global race among space agencies trying to understand it. The discovery of 3I/Atlas began in a way no one expected because interstellar objects are usually found too late for detailed study. On July 1, 2025, the Atlas system in Chile detected a faint moving point that did not match any known orbit. This tiny signal became the first clue that something unusual from deep space was approaching our solar system. Early detection gave astronomers months of preparation, and every new measurement suggested that 3I/Atlas was not a normal comet. The first clear images revealed a massive cloud of carbon dioxide stretching nearly 35,000 kilometers around the object. This surprised researchers because most comets release water ice, dust, and simple gases, while carbon dioxide rarely dominates the entire halo. A CO2 envelope that large did not match a nucleus only 1 or 2 kilometers across, and the mismatch forced astronomers to question the source of all that gas. Carbon dioxide can appear in distant objects, yet the volume around 3I/Atlas looked excessive even under generous assumptions. Spectroscopic readings added more confusion when the nickel-to-iron ratio appeared far outside the typical comet range. These metals hint at how and where an object formed, and the mix seen in 3I/Atlas did not resemble anything known in the solar system. Its organic compounds also differed from standard comet chemistry, creating a fingerprint that pointed toward an origin shaped by unfamiliar conditions. As the object moved inward, astronomers noticed brightness changes that did not behave like normal rotation or random surface activity. The rhythm looked too steady for a small icy body, suggesting that something structured might be influencing its light. This idea revived memories of the debates around Oumuamua in 2017. Yet 3I/Atlas offered a stronger signal because of its thick CO2 envelope. This made tracking easier for observatories in Chile, Hawaii, and Europe, allowing them to collect detailed readings weeks before the object reached stronger sunlight. As 3I/Atlas approached the inner solar system, it brightened much faster than expected, implying that far more material was escaping from the nucleus than its size could explain. Rapid brightening usually points to intense outgassing, but the observed numbers did not match any standard model. This raised suspicion that the nucleus might be hiding features that early instruments could not resolve. Major observatories prepared targeted studies, waiting for 3I/Atlas to enter a position where heat from the sun would reveal its true behavior. Researchers believed these observations could show how an interstellar object reacts to strong solar energy for the first time. Yet the early readings also created an unsettling thought. If 3I/Atlas was already behaving strangely at a distance, what would happen when it moved into a region where every hidden detail would be forced into view? That question leads directly into the next section, where the object's approach to the sun triggered a shift that challenged everything scientists expected to see. When 3I/Atlas moved deeper into the inner solar system, the numbers describing its motion began to drift far from what scientists expected. Its speed increased instead of slowing down, which confused observers because gravity normally forces a comet to follow predictable curves around the Sun. Acceleration measured from several observatories showed values that felt too strong for such a small object, and this strange behavior pushed researchers to look closer at every reading. Comets usually gain speed in a smooth pattern, yet 3I/Atlas showed sharp changes that did not match the model used to understand natural bodies. These changes suggested that something more than sunlight and gravity was shaping its path, although no one could identify the source. Outgassing is one possible explanation, since escaping gas can create a push that changes a comet's motion, but the results from Atlas did not follow the normal rules. The mass being released appeared extremely high, and the pace at which it changed surprised many researchers who tracked it night after night. Data collected in late summer showed a mass loss of hundreds of kilograms per second, which seemed large but still believable for a warming comet. 2 months later, however, estimates grew into the range of millions of kilograms per second, which felt impossible when compared to the size of the nucleus. Such a huge release of material would require a surface far larger than the one seen in earlier images. And this mismatch created one of the biggest puzzles in the study of Atlas. The object also began to glow with a faint blue light that did not look like the reflections seen on ordinary comets. This glow came from ionized metals, which become visible when extremely high energy interacts with their surface. Ionized metals can appear in some rare comets, yet the pattern recorded around 3I/Atlas did not match the usual profile and raised new questions about what was happening inside the object. Brightness data also revealed fast fluctuations that did not follow the natural rhythm caused by spinning ice. The changes felt too controlled, and the timing seemed too even to be a simple reaction to sunlight. These strange clues made astronomers wonder how a small interstellar object could generate such intense activity without breaking apart completely. The energy released did not match the expected amount of mass being lost, and this gap hinted at a process that has not been seen before. Some researchers proposed unusual chemical reactions, while others considered more complex internal structures that could behave differently when heated. Every explanation remained uncertain, and more readings were needed to understand what was hiding beneath the bright clouds surrounding 3I/Atlas. Even though the public had few details, scientists across several countries quietly increased their monitoring schedules as the object moved closer to the Sun. They believed the intense heat would expose the true form of Atlas, and they prepared to capture every second before it passed behind the Sun. Yet the strangest part of this story appeared only after those observations were complete. The idea that 3I/Atlas had broken into many pieces began when researchers compared its extreme activity with the small size of its nucleus. A normal comet cannot release such a huge amount of gas unless it has a large surface, so some scientists propose that the object might have fractured into several equal parts. This idea grew stronger when the early measurements showed a level of outgassing that seemed impossible for a single compact nucleus. If the object had split into many pieces, each fragment could provide more surface for sunlight to heat, which would explain the rapid rise in gas production. This theory gained attention because a group of 16 fragments would create enough area to match the numbers seen in the observations. The model appeared simple, but when astronomers examined the data more closely, serious contradictions emerged. Fragmentation normally creates a spreading cloud of small pieces, yet telescopes did not show a wide field of drifting debris around 3I/Atlas. Comets that break apart often leave behind large trails of dust shaped by the solar wind, but the region around Atlas looked surprisingly clean. Instead of a loose cloud, the images revealed concentrated forms that appeared too stable for an object that had supposedly shattered. These shapes maintained clear boundaries even while the object moved through a zone of intense radiation near the Sun. Such stability raised doubts about whether the object had fragmented at all, because broken pieces rarely stay close together in a consistent pattern. The lack of drifting dust made the theory even harder to support, since natural breakups usually produce clouds that expand for weeks. Another problem appeared when spectroscopic readings showed no major changes that would normally follow violent fragmentation. Fresh surfaces exposed by splitting should create strong spikes in brightness, but the rhythm of light around 3I/Atlas stayed unusually steady. This calm behavior did not match the chaotic signals expected from a shattered comet, and it forced scientists to question whether they were looking at something else entirely. The more they studied the structure, the more it seemed like the object was not tearing itself apart, but moving through stages with a strange level of order. Stable shapes appeared where disorder should have dominated, and this odd pattern made some researchers wonder if the object was maintaining a form that limited the spread of material. A natural comet rarely behaves in such a controlled way, especially under the extreme heat of the inner solar system. The attempt to explain these contradictions led to more ideas, yet none fit perfectly with what the telescopes recorded. Fragmentation could explain the high energy output, but it could not explain the lack of drifting debris. A stable nucleus could explain the clean surroundings, but it could not explain the incredible amount of gas being released. These conflicting clues made the theory unstable, and scientists realized they needed to consider new possibilities. Every new fragment of data suggested that something more complex was happening just below the bright cloud that covered the object. If the fragmentation theory could not explain the observations, then what process was shaping the strange forms seen around 3I/Atlas? That question leads into the next part of this investigation, because the most shocking evidence came not from theories, but from photographs that showed structures forming in real time. The most dramatic shift in the 3I/Atlas mystery began when astronomers noticed patterns that looked far too organized to come from a natural breakup. New images taken shortly after the object passed, the sun revealed a long, bright feature pointing toward the sun instead of away from it. This feature was an anti-tail, a structure that only forms under rare geometric conditions, yet this one had a sharp outline that stayed narrow instead of spreading like normal dust. British observers using advanced processing tools examined the faint details around the object and discovered multiple bright jets pointing toward fixed points on the ecliptic plane. One jet stretched hundreds of kilometers in a straight line without twisting, and its stability surprised experts who understood how dust normally scatters under solar radiation. The main jet reached a length greater than the distance between Earth and the Moon, making its clean shape even harder to explain with known physics. Other images from Europe confirmed that the jets were neither random nor temporary. A set of 7 bright columns appeared arranged in a pattern that looked symmetrical across the main axis of the object, something extremely unusual for a comet with an uneven surface. Symmetry repeated across several images taken from different countries, raising speculation that the release of material might be directed rather than accidental. A directed flow would require a mechanism able to guide gas movement with precision, and this idea pushed the discussion into concepts many astronomers avoided. But more images from Italy, Germany, and Spain continued to show identical geometric shapes forming around 3I/Atlas, making the pattern difficult to ignore. Brightness levels in the jets rose and fell on a regular cycle, which suggested that the activity followed a timed rhythm instead of random heating. Time jets have never been recorded on any comet since natural reactions rarely follow smooth schedules. The steady rhythm strengthened the idea that 3I/Atlas was shaped by processes that did not match known comet behavior. Small structures also appeared near the base of the jets, and their layered shapes made it look as if material was building upward in steps. This step-by-step growth contradicted the belief that the object was breaking apart and instead pointed toward a slow, organized rearrangement. With each new photograph, the evidence suggested that 3I/Atlas was changing itself with purpose. Yet one question remained impossible to ignore. If the object was building with such precision, what force was guiding the process? And that question becomes even more unsettling when we look at how major space agencies reacted in the following weeks. In the weeks after the first structured jets appeared around 3I/Atlas, the strangest reaction did not come from the object itself, but from the groups watching it. NASA released almost no public updates, even though the agency had shared regular reports during earlier interstellar events. This sudden change in communication caught the attention of astronomers who expected detailed data, especially after unusual activity became clear. Silence from a major agency can mean many things, yet in this case, it created a growing sense that something important was being held back. While NASA stayed quiet, the European Space Agency increased its observations using several orbiters that already had instruments ready to study objects near Mars. Missions such as Mars Express and the Trace Gas Orbiter shifted their schedules so they could track the object from unique angles. These adjustments were not announced widely, but observers noticed changes in public logs that showed the spacecraft pointing toward the region where Atlas was moving. The extra attention from ESA suggested that the agency wanted independent verification of the strange patterns recorded by ground telescopes. At the same time, reports from amateur trackers hinted that Russia and China were redirecting some of their high-orbit satellites to scan the area around the interstellar visitor. These satellites normally monitor communication signals or atmospheric activity. Yet their new paths lined up with the projected route of 3I/Atlas. No country confirmed these changes, but several observers who monitor satellite behavior noticed that at least 3 large craft had shifted into positions that allowed continuous coverage of the object. Such quiet adjustments indicated that multiple governments believed the situation deserved close attention. The increased monitoring raised more questions when radar stations in Europe and the United States detected a repeating echo pattern near the object's path. The signal was weak and could have been caused by interference, but its steady rhythm drew interest because natural noise rarely forms such consistent shapes. Scientists did not call it a message, and many stressed that the echo could come from reflections bouncing off the cloud around Atlas. Still, the timing matched the moments when the jets were brightest, and this connection made people wonder whether the object was reacting to something in its environment. Media outlets tried to obtain explanations from official channels, but responses remained vague, which added more weight to the idea that agencies were waiting for more data before making public statements. In global observatories, researchers worked long hours to prepare for the next round of measurements as Atlas moved toward a region where sunlight would hit it directly. They knew that this phase would reveal details that had been hidden inside the bright clouds surrounding the object. A coordinated plan was created by several institutions to ensure that no moment would be missed as the interstellar visitor approached a position ideal for clear imaging. The quiet race among agencies showed that no group wanted to be the last to understand what was unfolding in space. Even without official announcements, it became clear that the world's most advanced instruments were now watching 3I/Atlas with intense focus. Yet the deeper question remained unanswered. If so many countries were tracking the object at the same time, what did they expect to find once it reached the point where every secret would be forced into the open? The debate about 3I/Atlas grew louder when scientists realized that the strange jets and organized shapes could fit 2 very different explanations. Some researchers believed the object might simply be experiencing extreme natural reactions caused by the intense heat of the inner solar system. These reactions can force gas out of hidden pockets inside a comet, and the sudden release can create powerful streams that travel far into space. If the nucleus contains many chambers or layers, the heat could trigger several vents at the same time, which would form patterns that look complex from a distance. This idea suggests that 3I/Atlas could be a rare example of a comet with an unusual internal structure that behaves in dramatic ways when exposed to sunlight. Such a comet would still be natural, even if its reactions appear unfamiliar to observers who have only studied objects from the outer solar system. Supporters of this explanation point out that the inner regions of comets are difficult to understand because most missions have only explored small sample sizes. Natural variety could be larger than expected, and Atlas might represent a type of comet that humans have simply never encountered before. The extreme temperature near the Sun might also be forcing chemical reactions that produce strange colors or patterns in the gas around the object. These reactions could create a temporary order that looks designed even though it comes from physical processes. Others, however, looked at the same data and saw a different picture. The steady rhythm of the jets, the straight lines pointing toward fixed locations, and the symmetrical arrangement felt too precise for random heat changes. Natural forces usually create patterns that drift or fade, yet the shapes around 3I/Atlas stayed focused long after the object passed through the hottest part of its orbit. This level of stability led some researchers to consider whether something inside the object might be controlling the direction of the gas. Control would require systems that react to energy in a way that natural materials cannot easily copy, and this possibility started quiet discussions among scientists who usually avoid speculation. They noticed that the brightest jets appeared at moments that matched earlier cycles, and this timing raised the idea that the object might be following a programmed pattern. A programmed pattern does not require advanced technology. Yet the consistency suggested a process more complex than simple heating. If the object reacted to its environment by adjusting the intensity or direction of its jets, it could explain why the shape stayed sharp even when the conditions changed rapidly. Some astronomers began to compare the behavior of 3I/Atlas with known examples of engineered propulsion, although they stressed that there was no proof of such a system. They argued that the object might contain physical features that guide gas flow in a controlled manner, and these features could give the appearance of deliberate design. No one claimed that Atlas was a machine, but the idea that it might not behave like a normal comet pushed the debate into new territory. Both explanations remain possible, and each one raises its own questions. If the natural theory is correct, then Atlas shows physical behavior that has never been recorded before. If the guided theory is correct, then the object could be reacting to forces we have not yet identified. Astronomers knew. The final stage of 3I/Atlas's journey would be the most important because this was the last region where its real structure could be seen clearly. The short window created urgency, since anything recorded now would become the permanent record once the object disappeared into deep space. Hubble planned ultraviolet observations to capture the gases surrounding the nucleus and identify which reactions were shaping the unusual glow. These measurements would help scientists separate natural chemistry from signals shaped by unknown forces. The James Webb Space Telescope prepared its own campaign focused on heat rising from the inner layers of 3I/Atlas. If the readings showed strong internal warmth, it could reveal whether the object held a single core or several pieces working together. Ground observatories around the world also coordinated their schedules so they would not miss the moments when the jets reached their maximum brightness. Researchers expected the sun's heat to force hidden structures to appear inside the expanding cloud around the object. If sharp jets continued to form long straight lines, the new images could reveal whether the patterns came from natural vents or from something more controlled. Teams in Europe, Asia, and South America prepared their instruments to track the visitor from different angles to capture every detail before it moved too far away. Hubble's chemicals and JWST's temperature readings would give scientists the best chance to confirm whether 3I/Atlas had fractured into many pieces or kept a stable central form. A stable nucleus would challenge the idea of natural fragmentation, while a group of fragments would support the theory of increased surface activity. Scientists also compared the latest images with earlier data to measure how fast the structures were growing. If the jets continued to point toward fixed locations, the pattern would be difficult to explain with only sunlight and heat. Multiple agencies aimed their most advanced tools at the same point in the sky, turning this period into one of the busiest observation campaigns in modern astronomy. Oumuamua showed no jets, Borisov behaved like a classic comet, but 3I/Atlas carried features from both and added behavior that did not match either category. This unusual mix made the final observations even more valuable because they could reveal whether the object belonged to any known class or represented something entirely new. The world waited for the results, knowing this was the last chance to see 3I/Atlas before it slipped into the cold dark beyond our reach. 3I/Atlas is not breaking apart. Every new image shows it building structured layers from deep inside, as if the object is shaping itself with purpose. The jets stay sharp, the patterns stay stable, and the inner glow grows stronger each week. Some astronomers now believe its core may be reorganizing rather than collapsing. We might be watching the birth of something new, not the end of a comet. If you want to explore more strange discoveries shaping our universe, check out the other videos on mindgap and follow the trail of mysteries waiting for the next reveal.